welcome. This is a talk that's mostly about microservices, why you might want microservices, and some common pitfalls that you might encounter when you're implementing a microservice architecture, and finally some sort of methods to avoid those issues you might run into. The talk's broadly split into two sections. The first section, I'm going to be going over some of the problems that I've encountered in the wild with microservice architectures. These are some systems that I've worked with over the course of my career recently. And then in the second section, I'm going to demonstrate a slightly different approach to microservices, possibly to the ones that you've maybe heard of before, which can help to resolve some of the issues you might have encountered from the first section. Before I go into either of these items though, let's take a quick look at what we actually mean by microservices and why you might actually want to consider a microservice architecture for your software. So I've got two diagrams on the screen, and in blue on the left is maybe a typical monolith, and in yellow you've got something that looks more like a microservice architecture. The key difference is that in a monolith architecture you tend to have a single code base which encompasses the whole of your application's functionality, and with microservices or service-orientated architecture you tend to have lots of smaller little code bases with different data sources. And then you'll have maybe like some sort of front-end application which ties everything together. And you'll probably also see intercommunication between the various different applications within your stack. And they work together as a whole to form the whole system. So a monolith is generally what we call a single application. It will contain multiple business functions, and in general, all but the really largest organizations will tend to have just a single monolith application which deals with all their business needs. Monolith is often seen as a derogatory term, some legacy software which has bad design or is based on outdated methods. But this is really not true. It's perfectly possible to design a monolith application with good architecture, modular design, and such applications have perfectly good use cases and will provide business value to you. Another point about monolith is that it tends to be deployed and scaled as a whole application. This means that if you build a new feature for a monolith, you will build it through your CI pipeline and everything like that, and when it comes to release time, you will replace the entire application code base on your servers or on your production stack. Equally, if you have a burst of traffic, say after a successful marketing campaign where you get a whole load of new user registrations coming in, the effort to scale, you won't be able to scale up the registration part of your application to cope with that burst of traffic. You'll have to scale up the whole application, the whole monolith. Now in PHP this tends not to be as big an issue because the way the PHP request cycle works is that you only sort of load into memory the code that you're running. But with something like Java, where you tend to have big applications that are compiled, you tend to load the whole application into memory at once. That means that if you need a server with 16 gig of RAM to run your application, if you want to scale it, you've got to scale lots of 16 gigs of RAM virtual servers, and that can be more expensive than maybe scaling just a small microservice part that only needs 4 gig of RAM. Okay? Another point is that a monolith will generally be built on a single technology stack. This could be quite a broad stack, taking into account a couple of different data stores, Mongo, MySQL perhaps, and having both PHP and JavaScript code for the client side. But you'll generally find that it limits itself to, say, one PHP framework, Zend, Laravel, Symfony, and builds everything around that one sort of framework, essentially. To contrast, a microservice should have one responsibility in your software application, the system as a whole. It should do one thing, and it should do it well. Consider the Unix philosophy of having small tools which do one thing, ls, grep, and you can combine them to do more complex tasks, searching and filtering for files, for example. This could be quite a broad responsibility for a microservice. You could have a microservice which is completely responsible for everything to do with users or shipping. Or it could just provide a standardized standalone piece of functionality, such as an address lookup service. Both are valid potential options for a microservice. One key thing to note though is it should have full authority over that area of responsibility. If it's managing users, it shouldn't have to go off to another microservice to find out some information about a user. Everything should be local to that service. A microservice should be independent. There are several ways in which it should be independent. You should be able to deploy it separately to the rest of your application. So if you've got a feature for just your users microservice, you don't have to deploy your shipping and your customer relations microservice alongside it. You just do a release for the user microservice. You should also be able to change its inner workings without having to refactor and change the other microservices in your stack. If you decide that you want to refactor the data store that you're using for your users, that should not affect your financial microservice that's keeping track of transactions. It should be completely internal to that microservice. Microservices are always components of a larger system. They never act in isolation. So it's really important that each one of them defines a stable API through which other services can communicate with it. Our industry is quite keen on REST over HTTP at the moment, but don't feel your microservices should be constrained to this. RPC-based APIs are just as valid and, in my opinion, more useful in most cases. Or consider a microservice which accepts syslog formatted packets on a given port. That's still exposing a very useful API if that microservice is responsible for log aggregation. Okay. And finally, in contrast to some forms of service-oriented architecture, a key difference with microservices is the concept of smart endpoints and dumb pipes. Essentially, your microservices are where all the work and all the business logic happens. The communication channels between them are just that, channels of communication. Okay, so there shouldn't be any logic baked in with like smart routing components or things like that transform the messages between microservices. All the business logic should be contained within those microservice endpoints. Some of the key advantages of having a microservice architecture. Probably the first advantage that people cite when talking about microservices is that they help improve the modularization of your code. So microservice by their very nature cause the application to split across multiple different code bases. So this gives you a good opportunity to ensure that each code base is self-contained and only has dependencies sort of within itself. Okay. Another advantage of microservices is that it allows you to vary the technology stacks you base your application on and choose the best tool for the job that you're doing. This could mean a lot of different things depending on your organization. The most common change that I've seen is picking a different database. So if your main application is using MySQL, another microservice that's handling search might use Elastic as a back-end data store for storing data in, because that's more suited to the task of doing a search. The more adventurous sometimes even combine different programming languages and frameworks to take advantage of the different strengths and weaknesses inherent in different languages. Possibly the advantage that gives you the greatest benefit is your microservices can each be deployed and scaled separately. So if you do get that burst of traffic, or you have certain hotspots in your application, which say at the first of the month your finance application needs to churn through a load of account statements, you can scale that up separately to everything else. That tends to save you money, and then you can scale it back down again when it's done with the processing. Microservices also come with smaller code bases. This obviously means it's much easier for someone who is a new developer on your project to get to grips with how one application in your stack works, and they can become productive much faster when all they've got to learn is the code base for a single microservice. Additionally, with a smaller code base, it's much easier to justify throwing the whole thing away. If you've only got a small code base of a few hundred classes maybe, you can just say, well, that microservice isn't fit for purpose anymore, we're gonna throw it away and we're gonna write a whole new one. If you've got a huge monolith, you're not gonna do that. Some of the disadvantages then, of course, probably the biggest disadvantage of microservices is availability. If you've got a monolithic application and you can manage an uptime of 99.7%, that's pretty up. That's about 1 day's cumulative downtime over the course of a year. When you have 10 microservices with that level of availability, that means that each one of them is down potentially for a whole day in a year. And that works out that you've got a total across your entire system of 10 days of downtime. So that gives you a worst case, if it all happens sort of independently, of 97% uptime. So one of the key things you need to get right when you're doing microservices is managing to isolate them from each other so that if one microservice is down or having an error, it doesn't affect any of the others in your stack. Okay. A somewhat under-advertised disadvantage of a microservice architecture is that it can lead to knowledge siloing within your organization. If one developer is always responsible for the changes to the payments microservice, they become an expert for it. And this can lead them to being the go-to person for issues with the payment service. That means that they rarely see code in other services, and if each of your developers become an expert in one service, when one of them happens to leave the company or is just off on holiday for a few days, you're going to run into problems because no one else knows how a particular service works. So it's really important to try and keep developers active over as many different microservices within your system as possible to ensure that the knowledge is evenly distributed across your whole team. Testing can become quite an issue with a microservice system. There's a lot of failure cases to test for, and some of your system tests will need to span multiple services potentially to test what happens when the finance service sends an export to another service in your system. A lot of people ignore these system integration tests, but this can be problematic. If you've got two services, both which have fully green tests, the interaction between them still might not be working as desired, so the system as a whole might be broken, despite the fact that you've got a green build. And these issues can be kind of hard to track down and trap before you deploy code live, unless you've got some proper system integration tests. And finally, when you've got a monolith, orchestration of your deployed system is quite easy. You'll tend to have a few identical servers which serve your application, maybe a few identical database servers, and that's quite easy to manage because you've got sort of one configuration for your application, one configuration for your databases. A microservice architecture, on the other hand, has lots of moving parts. You've got lots of different separate services, each which might have slightly different configuration requirements. And so this gives you a whole set of new problems, like ensuring that they can find each other on your network and communicate properly, doing backups and logs to a single central place so that you can store them and parse them effectively. So you've got a lot of things to think about on how to actually aggregate all this information and make sure your system works smoothly as a whole. You'll find tools like Chef and Ansible and all those kind of things really invaluable when you're dealing with microservices. You can probably get away without those kind of things if you've got a monolith, maybe. But you won't be able to do so if you're using microservices as an architectural pattern. So the one thing I haven't touched upon yet is part of the title of this talk, which was the distributed monolith. A distributed monolith is a term which is used to describe a system which initially looks like a microservice architecture, but it's actually a monolith in disguise. What tends to be wrong with this? Well, generally you end up picking up the disadvantages of both architectures. You've got this big, huge, cumbersome code base, but you don't get the advantages of having either of the so you don't get the ability to scale separately quite often because one service will sort of knock on to the others. And so this section of the talk is going to look at a few of the warning signs that you might actually be building a distributed monolith instead of a true microservice architecture. One thing I will say is don't panic. You might sort of feel after this section of the talk that microservices are like a hugely bad idea that you should never ever implement. But the issues that I've sort of accumulated in this section have come from lots of different systems. They weren't all on the same one. So hopefully you don't have all of these problems in your systems at the moment. Otherwise, well, hopefully you'll be able to fix them after this talk. So, number one problem I've come across, and this is probably the most common mistake, is the common library. So we'll do a quick show of hands. Who here currently has some form of microservice architecture in their organization that they're working with? Okay, few people. So keep your hands up if you have a common library that's shared between them. Yeah, there's quite a few there, yeah, a few nodding heads. The reason it's such a common mistake is partly just the way it comes about. Someone thinks it's a really sensible idea to group some common abstracts and some common utility classes into a library that you can reuse across all your microservices and keep things consistent. The library ends up growing over time. Whenever something needs to be shared between two microservices, it's like, all right, just put it in the common library. The effect of this is that common library becomes much, much bigger over time. But it takes a long time for the problems inherent in having that common library to become apparent. They kind of sneak up on you, and what originally helped speed up your development now slows it down, and it does take quite a bit of work to resolve. Why is it so bad? When you start to build up a body of code inside a common library, the microservices lose their independence from each other. This initially exhibits as a minor inconvenience when you implement a feature that requires a change in the common library as well, meaning you've got two windows and your editor open, you've got to make two pull requests, you've got to synchronize it and make sure that everything goes out. But the pain really becomes apparent when you make a change to the common library for one microservice. You do a deployment, everything's green, everything's working. A week later, you deploy a different microservice which also depends on the common library. That goes out and everything breaks because it wasn't expecting the change in your common library. The common library, when it becomes shared between most of the microservices, it becomes a dumping ground for shared code. Your small, lightweight microservices might look initially lightweight because they've got this small code base inside their individual code bases, but they're backed up by this huge common library, which, in order to be productive in developing a microservice, a developer's going to have to understand at least some of the code in that library as well. So you start losing the benefits of that small code base. It also changes so fast that normal versioning goes out of the window. Instead, you have a dependency on devmaster in your composer.jsons, and this reduces the reliability of the builds and makes development workflows using Composer quite awkward. This happened on a project I was on a couple of years ago. We had a common library shared between two services, and we relied on devmaster, and it was every pull request had a change to common and a change to one of the services. So it was rapidly evolving, and it became a nightmare to manage. And once you build up a huge library of code on which your microservices are based, the perceived cost of bringing in a new language or even a different framework looks huge. So if you're like, well, this other language would be really useful for this problem, you've kind of got this blocker that you sort of say, well, if we move to this new language to use this platform to do this problem, we're going to have to rewrite this entire common library in your new chosen language. It acts as an artificial barrier to adopting these new technologies. Okay, so it kind of like limits you sort of artificially in that way. So what's the solution? So instead of creating a huge common library with everything in, try instead to stick to smaller focus libraries. If you've got a HTTP client library that you use, make that a library on its own. Okay, the smaller libraries will change far less often, and you can use semantic versioning to manage their changes, which will help stop breaking changes going out in microservices. They'll also be easier to port or reuse should you change your framework or language of choice in the future. You may initially find that this worsens the multiple pull request problem, because sometimes you might have to put pull requests onto several libraries to make a change, but it's easier to sort of define the new feature in terms of make this change to the HTTP library, you can put that in, put a pull request in, make sure it's all tested, then you can move back to your microservice, update the dependency, and make your code change in there as two distinct separate tasks, rather than having to work on them at the same time. Each microservice can then only include just the libraries it needs. This reduces the bloat inside each microservice and shrinks your codebase size down, and it also prevents some unexpected surprises when you accidentally deploy out a huge library with a security flaw in, for example, which wasn't actually being used by that microservice. Some of you will be listening to this and wondering, how on earth do you manage dozens of these private internal libraries? Surely this is far more work than a huge big one. Well, Composer is a really great tool for managing this problem. You can lock the dependencies down and ensure reliable builds. And you can also use tools that come from Composer to keep track of the available versions of your internal libraries. There's Satis, which is a sort of free self-hosted kind of micro-packagist. There's Toron Proxy as well, which can sort of act as both packagist and a sort of a caching layer. And there's also a private packagist, which is recently launched, that you can actually use as your organization and keep private packages on. So you've got a few options there to help you manage them. And finally, sometimes it's contrary to every programmer's basic instincts, but copying and pasting code from one application to another is often a safer and cheaper solution. This allows the two initially shared bits of code to evolve separately without risking the stability of the service you originally pulled it in from. Instances where this works quite well, I found, is if you've got something like an abstract controller class which contains some helper or utility methods. If you copy that into your new microservice, then you can add new utility methods that are specific to that microservice. without having to change the shared one that's across the remainder of your services. The next pitfall we'll have a look is interdependent deployments. So another of the common pitfalls that microservices get into is a situation where you end up needing to synchronize deployments of multiple microservices. This could be to do with a breaking API change or something like that. And it's one of the problems that has a huge scale in how much pain it causes you. On one end of the scale, a client I was working with had to delay the release of a front-end application change because the back end for it wasn't quite ready yet. And it caused them a couple of days delay on releasing a front-end change that was completely unrelated. It didn't have a massive impact, it was just a bit annoying. On the other end of the scale, a company that I worked with a little bit more recently had a huge microservice platform. And in order to get a working development environment, you had to spin up each of the microservices in their system in a specific order. Otherwise, it didn't work. Just for fun and games, this wasn't documented anywhere either. So they brought a brand new team in of 3 rather highly paid contractors who then spent a week trying to figure out how to get a working development environment. That costs a lot of money. To give you a visual indication of how this might be a problem, imagine for a moment that you've got a monolith to deploy, okay? Just the one thing to keep your eye on. Now, even if something gets a bit complicated, it's still quite easy to do, right? Now imagine that you've got 3 microservices that are all dependent on each other, and whoops, deploying them becomes a lot harder. You've got a lot more things to keep in the air, a lot more things to keep your eye on. And if that isn't bad enough, just think about what might happen if you're on call. 3 a.m. in the morning, call comes out, you've got to fix something. And you've got to manage that deployment of 3 or 4 microservices, keeping them in the air. It's as if the juggling balls are on fire. Unfortunately, I can't demonstrate that because we're inside and I dropped one already, so that would have been bad. So you sort of get the idea of how that sort of can cause you some issues. Obviously, with each simultaneous deployment that you're having to do at once, I mean, in the worst case of that client where they had to deploy all of them out in one go, each one increases your risk of sort of dropping the ball and having a production outage, okay? With more to concentrate on, it's more likely that the person doing the deployment will start skipping important steps like testing each of the newly deployed services properly, which can obviously lead to further problems in live. Possibly the worst side effect of interdependent deployments comes when you do a deploy that's broken and you need to roll it back. This is fairly easy if it's the first service you deploy it out and it's broken, you go, oh well, roll it back. But if you've just deployed 7 services to live and the last one's broken and you need to roll back that whole thing, that's another act of juggling, but you've got a production outage at the same time. So there's even more pressure and you even are under even more stress to get that system working again. So what can we do about it? The first and most obvious way to avoid this problem is by versioning the APIs that the microservices communicate with. That way you can deploy a new version of your microservice, but make sure the old API is still available so that the other services in your stack can say, well, I only know how to speak version 2 to that microservice, I'm going to use version 2, whereas a newer deployed microservice might say, well, I know how to speak 3, so I'll use version 3. This introduces a little bit of extra complexity, but it does allow you to decouple the deployments from the API changes. There's also another option you've got is when even the best designed versioning scheme will require some breaking changes and require you to deploy several services at once. For example, the first time you deploy versioning on your APIs, you'll probably need to do this. The easiest way to deal with these situations is using feature flags. What you can do is you can deploy some code with an if statement around the new breaking feature and a flag. And then once you've got all the microservices deployed out and you've tested that they're working with their old behavior, you can flip that flag globally across your entire infrastructure, maybe storing it in Redis or a database or something like that. And that turns on the change for all of your microservices all in one go. If something's broken, it's easy to roll back just by turning that off. And you can still deploy each of your services separately from actually changing that feature on. Another option, if you really have to deploy lots of microservices at once, is automation. The more automation you have around your deployments, the better. This should really be considered a last resort, but in the worst situation, if deploying all 7 of your microservices is just clicking one button in Jenkins, you might be okay, maybe. Okay? Last of the pitfalls that I'm going to go on to. The first 2 were fairly easy to avoid with a bit of careful planning and development. But this one, it's really big problem sometimes. Both a common library and interdependent deployments are examples of coupling between microservices, but temporal coupling is by far the most damaging to your system. So what exactly do I mean? Imagine you've got a ticket booking application, okay? Something for booking concert tickets, and a user wishes to purchase a ticket. So on your nice JavaScript-y front end, they submit a form with their card details, the number of tickets, and the concert they want to go to. And then the server application then makes REST calls to the user service to check the login, receive user details, the ticket microservice to check that the tickets they want to buy are available, the fraud microservice to make sure that they're not using a stolen credit card or anything like that, the payment microservice to take a payment, the ticket microservice again to record those tickets as sold now because you've sold them, the accounts microservice to log the sales so that you can do some financial analytics and things like that on it, the loyalty service to update the customer's loyalty points, the email service to send a confirmation email. That there is a huge distributed monolith. Okay, all you've done is you've got lots of modules in your code, and instead of having them contained in one codebase, you've distributed them across a network. Okay. What makes this so bad? The first thing you're probably going to notice about this, if you're making all those HTTP, TCP connections between your services for one user request, is that it will be really slow. To sort of illustrate how slow that can be, in PHP, a method call overhead onto a class is measured in microseconds, whereas a network call between microservices, in even the best cases, is measured in either tens or hundreds of milliseconds. That's 100,000 times slower. Okay? This tends to creep up on you slowly as your functionality grows. I had a software application that I was working on, and to render one page, we ended up with something like 14 back-end calls, and that page took about 15 seconds to render. It's kind of bad. We fixed that eventually, but the business were not happy with having to wait 15 seconds for pages of their system to load. In the previous example that I showed you, everything happened synchronously. Each service had to wait for a response from another service before it could continue with processing the request that it was doing. So just a single service failing in that sort of transaction of things, if your loyalty service was down, that could bring your entire ability to book tickets to a halt. Okay? So having to wait for a response between these calls is kind of bad. And what happens when something fails? The number of failure scenarios grows exponentially with every additional service call. So for example, at each stage, some business logic could fail. The tickets are sold out, or the customer doesn't pass the fraud check. But you can get a more sort of insidious failure mode. What happens when you've taken payment for the tickets and you send a request to the tickets microservice to mark those as sold, and it times out? What happened? Did it mark them as sold or not? Are those still available? How do you recover from that situation? There's no way to sort of know if it succeeded or failed. Okay, so it can get you into situations which are really hard to recover from, at least automatically. Distributed transactions are really, really hard. Okay, doing things which require consistency across multiple nodes in a system is really difficult. It's a really huge engineering problem. Trying to figure out what to roll back and the order in which to roll things back when you're sort of halfway through booking some tickets in that system I showed you is really difficult. And what happens if you get a failure of one of the services while you're trying to roll it back? That gives you an even bigger problem. So distributed transactions are something you really want to try and avoid. So to sum up that subsection, you may notice a common theme. They're all examples of coupling between the microservices. Just like coupling to a framework in your code can cause you problems when you need to upgrade it and things like that, having coupling between microservices can also cause you a major source of problems. It can really slow down your long-term velocity in developing new features, which is kind of the opposite of what you really want when you're trying to move to a microservice architecture. So if coupling between microservices is so bad, what could we do to avoid it? Often there's a misconception around the term microservice and the application of the single responsibility principle. People take this to mean that a microservice should do only one thing. That kind of thinking leads to microservices like address, invoice, etc., which consist of a single domain model behind a REST API. That means that any transaction that involves an address, for example, adding an address to an invoice, has to necessarily involve two services. That's bonkers. Okay? The trouble with microservices is that they are too fine-grained. It involves lots of services in a single request. It's perfectly acceptable for a microservice to have a fairly broad responsibility, user microservices, as I suggested at the beginning, and be responsible for everything to do with that user. It can store the user's address, that's fine. You don't need an addresses microservice. There's also nothing wrong with a microservice having its own API, having its own UI, not just an API. So if you've got things like forgotten password and registration, the user microservice could actually serve up the HTML and JavaScript and things like that for that function. Then you don't have to involve any other services. It's just that microservices that's handling that transaction. Define clear boundaries between your services. If you define a clear boundary and a clear responsibility for each of your services, the need for them to communicate with each other diminishes. Ideally, it should be possible for a single microservice to handle most user requests, avoiding cross-communication between them while a user is making a request entirely. This won't always be possible, but the closer you are to it, the better your overall experience will be. Obviously, the boundaries can be hard to get right up front, which is another reason to avoid making your microservices too small to start off with. It's much easier to split a service that's gotten too large than to try and stitch several back together. Best way of avoiding temporal coupling is to try and communicate asynchronously. This requires a bit of a shift in thinking from REST-based APIs, and it's what I'm going to focus on for the rest of the talk. Okay? So, second section of this talk is about event-driven and message-driven architecture. In brief, the idea is that instead of making REST calls between each of your services, services will instead exchange state with each other through events, things that happened. Does that sound familiar to anyone? A few nods. You might recognize this idea representing state as a stream of events from event sourcing. There's quite a lot of overlap between the two. The main difference is the scale. If you've got an event source architecture, you're looking at a single class, a single model within inside your system. Whereas with event-driven stuff, we're sort of zooming out and looking at the system as each microservice becomes a sort of a system which produces and consumes events. It isn't necessary to use event sourcing to use event-driven architecture, and even if you did, you would probably be using different events at the lower level than at the higher architectural level. There would be physically different events. But it does have an idea to have a basic idea of what event sourcing is. So a quick recap for anyone who's unfamiliar with it, because it's quite a niche topic. The diagram on the slide shows a traditional relational database model of a shopping system. We have tables which store line items, things that are in your customer's basket, customers, and your app will update, delete, and insert from these tables as a customer progresses through the order process. Contrast that with a more event-sourced approach, and you have events. So each time when a user starts off, they create an order. That's an event, the customer Tom. Tom adds an item to his basket. So we've got an event which says this item code, quantity 1, has been added to the basket. Then he adds another item, that becomes another event. Decides, actually, I didn't want an item after all, so removes it. Maybe updates the quantity of an item, that's another event. And finally, he checks out. That's another event. The system is using the events to keep track of the progress through that process. Now, if we wanted another microservice to know about some of these events, we could publish them to a queue, and that microservice could then listen to those events and react appropriately. In reality, you're probably going to have all those events on that slide internal to your orders microservice, and then you'll probably publish a user order has been checked out event to your queue, and that would allow other services in your system to react to that event and do what they need to do about it. That might look a little bit like this. So if we have a look at that ticketing booking service again, instead of having them all sort of connected crisscross with REST API connections, we connect them all to a message bus. That looks a bit like this diagram. Whenever a microservice processes some user input which causes a change that, as a developer, you think that other microservices need to be notified about, they publish a message to the bus and say, you know, this user has ordered some trainers, okay, or some tickets. And then each microservice that listens for events that it's interested in. So your ticket booking service has processed that order. The loyalty service listens out for that thing and says, okay, I've received that event. And asynchronously, it says, I'm going to add some loyalty points to that user. Your email service also is asynchronously listening for that event. When it receives it, it sends out an email saying, thank you for booking with us. Here are your tickets. Okay, so that becomes a lot more easy to reason about and manage, because you're not making all these calls all over the place. To make all of this work together, there's a couple more concepts from event sourcing that we need to borrow. The first is a projection. The idea of a projection is that when you get those messages, you've got an event listener which listens to those and turns it back into the relational database model that you're maybe more familiar with and you're actually operating with. So you get an event in and you store that data in a way that your application, the way that microservice wants to work with it. That's a projection. It could be a MongoDB document in one microservice, a relational database table in a different microservice, maybe Elasticsearch or some other data store. So what you project into depends on the use case for that microservice. If your microservice goes down for any reason, perhaps while you're deploying a new version, or just because it's gotten way too many requests in and it's fallen over, it needs to catch up with any events that you've missed. It may be possible, depending on your queue implementation, Kafka is quite good for this, to smooth over short gaps by just buffering messages up and then sending them when the service comes back online again. But for longer downtimes, you might need to consider other options, such as being able to fetch those events synchronously as a part of your bootstrapping process during the deploy. An important feature of projection is you can actually throw it away and rebuild it. So this could be due to you finding a bug in your code that is writing the wrong records to the loyalty table. So you throw away your loyalty table, points table, and you replay all the events that it's received from the start of time. And then you can rebuild that loyalty table with the bug fixed. And maybe fix some point balances that might be too low for your users, for example. Obviously, when you're dealing with events coming from a remote service, you're going to need to have a mechanism to get those events. I'm going to go into more detail about how you might do that in a few moments. The other thing that we might need to consider is a process manager. In contrast to a projection, which creates a read model for an event, a process manager will handle business logic that stems from the events. So, for example, this could be as simple as sending an email to the accounts department whenever an invoice is raised for over £1,000, so they can check it and make sure it's correct. That's a piece of business logic. When an invoice received event happens, have a look at it. Is the value over 1,000? Yes. Here's an email to the accounts department. It could be much more complex, that results in actually new events being published to the message bus. An example of this might be a loyalty system where you're sort of cycling through and getting a £10 off voucher after 3 purchases. The best way to think about a process manager is as a state machine. For any business process, receiving an event causes a transition to a new state. Consider a referral scheme: 3 friends, and you get a £10 voucher. You have a state where you've referred no friends, a state with 1, a state with 2, and finally the third state, which is where you send out the £10 voucher. Each event causes a transition from one state to the next. Projections are generally quite easy to replay because they're just a read-only model, effectively. But process managers, because they interact and can potentially make changes elsewhere in the system, you need to be very careful when you're replaying them. Generally, you don't tend to replay them at all. Okay. So I said I'd talk about this, replaying events. I found the best way of handling this is sort of outside the usual queue. So you might implement just an API endpoint on each of your microservices which says, get me the events that you've published since a particular time. And that means that whenever your service goes down for any period of time, it can say, well, I'm interested in events from the ticket system. So I'm going to call its API endpoint and says, give me the events I've missed. Okay? When a service needs to replay events for rebuilding a projection or producing a new projection, you can use the same API endpoint. You say, give me all the events since the start of time. And you'll get them back in a stream, you process them, rebuild your projection, and then bring your service online. Advantages of this architecture pattern is that it decouples your microservices from each other. Instead of like talking and saying, ticket service do this, loyalty service do this, they tell each other about what they've done and let each service deal with that itself. Such a system also allows small amounts of downtime between your microservices without a great effort on without an effect on your frontline service to users. So it improves your availability. It scales quite well. Another advantage of it is that if you need to deal with a spike in traffic, you get a load of events queued up on your bus. Even if a service is slow and churning away at the back, it doesn't affect the performance for your front-end services. It just has a backlog, and your emails will get sent out eventually. Okay? Another interesting point is if you wanted to add a brand new service, you can do so without impacting capacity of your initial services. That can just listen to the events again. It's not making more calls and putting more traffic onto your existing microservices. Another thing that you can do is, if you need to add new features, auditing, for example, you can do that by just listening to the bus and processing those events. You don't have to go back and change each of those microservices to add a new feature. You can just listen to events off the bus and add a new microservice which does it, instead of having to implement that feature in your microservices that are already existing. You no longer need to handle distributed logic. Handling rollbacks and failures of individual microservices becomes much simpler. If something goes wrong, you just raise another event. So if someone fails a fraud check, you raise an event, failed fraud, those tickets can be put on hold, customer services can be alerted, they can check into it and ultimately cancel the purchase. Okay? Much easier than trying to figure out, did that time out, did that work, did that roll back properly, etc. So we've taken a brief look at how microservices and monolithic architectures differ and why you might want to use both of them. I've also covered some of the common mistakes people make when implementing them, and hopefully giving you some tips for how you can avoid those mistakes. And finally, we took a brief look at how we can use asynchronous events between microservices to further improve the autonomy of a microservice. I'm now going to go through what I think are the key takeaways from this talk and things to consider if you go down the route yourself. Every architectural pattern involves trade-offs. The most important thing to take away from this talk is to know what those trade-offs are and make informed decision about their cost benefit to your unique problem. Okay, don't just say one size fits all. You know, Netflix are doing microservices, so we've got to do microservices. It might not work for you. Some of the trade-offs are clearly worthwhile. Others may be made because when people are very close to a problem, they rationalize a trade-off as being better than what they had before, and maybe don't consider changing track when something isn't quite working. The choice between a microservice and monolith is no different. It is a choice. It's a trade-off. You need to make it. Start big. A point which bears repeating is that microservices are so named because they are micro in compared to the monolith they are replacing. It is not a judgment on the specific size of any service. It's always better to start off with something that's big and split it down as you learn more about the problem that you're solving, because you'll make better, the more you know about the system you're building, the better decisions you'll make about where those boundaries lie. If you already have a monolith, it's an excellent place to start to build microservices. Find a self-contained area of functionality, maybe an address lookup service, for example, and break it off into its own little microservice. See how it works. Continue with this pattern until you have a microservice architecture. Favor autonomy over the single responsibility principle. Many of the problems you'll run into when building microservices comes from a high degree of interaction between the different microservices. This can come from overzealous enforcing of the single responsibility principle. It can be a trade-off well worth making to put a seemingly unrelated piece of functionality contained into a microservice when it's the only one to use it. It might not be related to that function, but if it's the only microservice that needs it, it might be a reasonable trade-off to just embed it inside that microservice for the time being. Remember, you can always break it out later if another microservice needs to use it. Embrace eventual consistency. Perhaps a controversial point, but if you're building a microservice architecture, embracing eventual consistency is a great way to save yourself a lot of headaches. The real world is eventually consistent. Imagine you've got a warehouse and your computer system says there are 10 TVs in your warehouse. Unbeknown to you, someone's stolen one. How many TVs do you have in your warehouse? 9. But your computer system doesn't know that. You can easily, if you've got an e-commerce site, you sell 10 TVs and your employee goes to get the last one and goes, oh. Your computer system being completely consistent didn't help save you from that problem. So you might as well use that to make your engineering problem simpler. Business processes were eventually consistent before they were computerized. Imagine a form for an order. It'd go from the sales guy, they'd fill out what they wanted, they'd stamp it, sign it, then it'd walk across the office and put it on the desk of the accountant's person, and they'd pass this document around until that order got shipped out. That's eventually consistent. There was no central place where all these records were kept until the order was completed. So that's bringing that into the computing world. There's no need for microsecond accuracy in your data. You can take advantage of this when you're implementing services. And each microservice should maintain its own worldview. It shouldn't need to go off to another one to get data. If it wants to know something about a user, save it in its own data store. Okay? So it can look it up locally, rather than having to go off to the user microservice to find something out. Okay, that's everything. So, all right, thank you very much. If anyone wants to have a look, the slides and a couple of videos of this talk are up on my blog, github.io. And there's a joined in link as well if you want to give some ratings.